in the following form: x2 plus a1n xn equal to b1, a21 x1 plus a22 x2 plus a2n xn equal to b2, and like this am1 x1 plus am2 x2 amn xn equal to bm. Let it be A. A can be written in matrix form as Ax equal to B, where A is the coefficient matrix A11, A12, A1n, like this AM1, AM2 and AMN. X is n cross 1 vector and B is the constant vector, that is B1, B2, like this, Bm. This is n cross 1 vector, this is m cross 1 vector. Now the system A can be consistent or maybe inconsistent. What does it mean? The system A is consistent if it has at least one solution, and the system is inconsistent if it has no solution. Now let us consider some examples. One is, consider the set of lines as x plus 2y equal to 5 and 3x plus 6y equal to 13. The system has no solution. Why? Because if you draw the graphs of these lines, draw the lines on the graph on the xy plane, you will get two parallel lines that doesn't intersect at a common point. Hence this system of equation has no solution. Second example, consider x plus 2y equal to 5 and 3x plus 5y equal to 14. Now this system has exactly one solution. If you draw its graphs on xy plane, the lines intersect at a common point that denotes their solution point. Next, third is x plus 2y equal to 5 and 3x plus 6y equal to 15. Now, if you draw the graphs of these lines on xy plane, the lines coincide. That is, every point that lies on the first graph also lies automatically on the second graph. Hence, we can conclude this system has infinitely many solutions. Now I will discuss Kramer's rule. Kramer's rule is a theorem in linear algebra which gives the solution of a system of linear equations in terms of determinants. Given a system of linear equations, Kramer's rule is a handy way to solve for just one of the variables without having to solve the whole system of equations. According to Kramer's rule, a system of n linear equations in n unknowns, that is Ax is equal to b, where determinant of A is not equal to 0, then there exists a unique solution of the system given as x1 is equal to determinant of A1 divided by determinant of A, x2 is given as determinant of A2 divided by determinant of A, and similarly xn is obtained as determinant of an divided by determinant of A. Now what ai represents, where I is equal to 1, 2, like this n. Here ai is the also n cross n matrix obtained from A by replacing its ith column by the constant vector b1, b2 and bn. Just replace the ith column by this constant vector. Let's take an example. Now solve the system of linear equations given as 3x1 plus 2x2 plus 4x3 is equal to 7, 2x1 plus x2 plus x3 equal to 4, x1 plus 3x2 plus 5x3 equal to 2. Now, here the coefficient matrix A is given as 3, 2, 1, 2, 1, 3 and 4, 1, 5. First, we will apply Kramer's rule if determinant of the coefficient matrix is not equal to 0. What is the determinant of A? That is equal to 3 into 5 minus 3 minus 2 into 10 minus 1 plus 4 into 5, that is equal to 8, which is not equal to 0. Since determinant of the coefficient matrix is not equal to 0, here Kramer's rules can be applicable. And applying Kramer's rule, we get x1 is equal to, as the numerator, x1, that is column 1, determinant of a1, that is column 1, is replaced by this constant vector and other columns remains as it is. So we get 2, 1, 3, 4, 1, 5 and below determinant of a. After expanding, we get x into 5 minus 3 minus 2 into 20 minus 2 plus 4 into 12 minus 2 divided by determinant of a, that is 8, and calculating it we get 9 by 4. Similarly, x2, in case of x2, the determinant in numerator is first column as it is, second column we replace it by the constant vector 7 for 2, and third column remains as it is, and then denominator we write determinant of a. After evaluating, we get it as 9 by 8. Similarly, x3 can be written as numerator 3, 2, 1, 2, 1, 3, third column replaced by the constant vector, and in denominator there is determinant which is equal to 5 by 8. Hence, Kramer's rule is not applicable if determinant of coefficient matrix is 0. Now, what will happen if the system is homogeneous system, that is Ax is equal to 0. So, in this case, this is a homogeneous system, Ax is equal to 0. Another case is that Kramer's rule, we are applying Kramer's rule in a case of system of linear equations where there are n equations and n unknowns, that is the coefficient matrix is square matrix. Now, what will happen in this case? Ax is equal to 0. Case 1 is 2 case are there. If determinant of the coefficient matrix is not equal to 0, then by Kramer's rule, this homogeneous system admits of a unique solution. Unique solution. Let we represent this homogeneous system by P. Then P admits unique solution which is 0 solution. That means x1 is equal to 0, x2 is equal to 0, and like this xn equal to 0. Now, what is case 2? If P has a non-zero solution, then we can write determinant of Aij is equal to 0. Next, I will discuss 3 cases of existence and number of solutions of the non-homogeneous system Ax is equal to B, where A is an m cross n matrix. Case 1 is m equal to n. Here m is equal to number of equations and n is the number of unknowns. Now, when m equal to n, that is number of equations is equal to the number of unknowns, that is the coefficient matrix A is a square matrix, then the system is consistent when rank of the matrix is equal to the rank of its augmented matrix. Now what is augmented matrix? Here consider the system as this: A11 x1 A12 x2 equal to B1, A21 x1 plus A22 x2 is equal to B2. Coefficient matrix A is written as A11, A12, A21 and A22, whereas the augmented matrix is written as A11, A12, B1, A21, A22, B2. Now, in any case, a system is consistent if and only if rank of the coefficient matrix is equal to the rank of augmented matrix. Suppose this is true. Then we will consider two sub-cases under case 1. That is, when rank of A is equal to rank of A bar, that is equal to n. Then we can say that A is non-singular. That is, determinant of A is not equal to 0. And we can say that the system has unique solution. So in this case, determinant of A is not equal to 0. That means the matrix A is non-singular, and then only the system will have an unique solution. And the subcase 2 is rank of A is rank of A bar, that is, the system is consistent but it is less than n. Then in this case, the associated underlying homogeneous system, that is Ax is equal to 0 when all Bi's are 0, has infinitely many solutions. Hence, therefore, Ax is equal to B, that is the system of non-homogeneous system, also has infinite many solutions. So, these are the two sub-cases. Now, consider case 2. Having infinite many solution is also means the system is consistent but don't have any particular solution but has more than one solution. Now case 2 is m is less than n, that is, number of equations is less than number of unknowns. In this case, the system is consistent if and only if rank of A is equal to rank of augmented matrix, that is less than equal to m. And in case of consistency, rank of A is equal to rank of A bar is always less than n. If the case is consistent, then the underlying associated homogeneous system has infinitely many solutions. And therefore, the non-homogeneous system also possesses infinitely many solutions. Now consider case 3, the last case, that is when m is greater than n, that is number of equations is greater than number of unknowns. The system is consistent if and only if rank of A is equal to rank of augmented matrix, that is less than equal to n. Now we will consider again two sub-cases. One is the system is consistent, that is rank of A is rank of augmented matrix, but this is also equal to n. Then the associated homogeneous system possesses only the zero solution, that is x1 is equal to 0, x2 is equal to 0, like this. And therefore, the system, the non-homogeneous system Ax is equal to B also possesses only one solution. And what is subcase 2? Subcase 2 is the system is consistent. The criteria is rank of A is rank of augmented matrix, but that is less than n. In this case, Ax is equal to 0 possess infinitely many solutions, and hence therefore the non-homogeneous system that we are discussing possess infinitely many solutions. We will apply these cases to different problems and we will see whether a given system of equations has many solutions, no solution, whether the system is consistent at all or not. Consider an example. Solve x plus 4y equal to 2, 2x plus 7y equal to 5 and 4x plus 9y equal to 15. See, here m is equal to, that is number of equations is equal to 3, and n, the number of unknowns, is equal to 2. Hence, in this case is applicable where m is greater than n. Now, first we will consider the augmented matrix, that is equal to 1, 2, 4, 4, 7, 9, 2, 5, 15. First we will check whether the system is consistent or not, and for that we have to calculate whether the rank of the matrix and the rank of the augmented matrix are equal or not. Hence, on this we will apply some elementary row operations, that is R2 minus 2R1. That is, we are subtracting 2 times of elements row 1 from elements of row 2. And similarly, we are subtracting 4R1 from R3. We are doing all these operations on the augmented matrix in order to calculate the rank of the matrix by applying the method 2 that we have discussed before in discussing how to calculate the rank of a matrix. Hence, we get here 1, 0, 0, 4, minus 1, minus 7, 2, 1, 7. Next, we apply another row operation, that is minus R2, that is we are multiplying row, R2, elements of row 2 by minus 1, and we are getting this as 1, 0, 0, 4, 1, minus 7, 2, minus 1, 7. Put a bar here that will differentiate the rank of coefficient matrix and rank of augmented matrix. Next, again apply some other elementary row operations so that we get row reduced echelon form of the given matrix, that is R1 minus 4R2, R3 plus 7R2 to make these two elements 0. As we know the method 1, 0, 0, 0, 1, 0, 6 minus 1, 0. Now we get row reduced echelon form, from which we can calculate rank of A as equal to number of non-zero rows here is 2, so this is 2, and rank of the augmented matrix, number of non-zero rows, that is 2, so this is also equal to 2. Hence, from this 2 equality, we can say that the system is no doubt consistent. But whether the system will have unique solution or whether it will have infinitely many solutions. So, here subcase 1 is applicable. So, here rank of A is equal to rank of augmented matrix, which is equal to n, that is equal to 2. Hence, clearly, if we apply this subcase 1, this system of equation has only one solution. In case if this is less than n, that is less than 2, then only we can say that the system would have infinite many solutions. But here this case is applicable. Next, consider this problem where value of A is unknown. We have to solve this system of linear equations. First our task is to write down the augmented matrix. That is 1, 2, 3, 1, 3 minus 2, 1, 4a, 1, k plus 2, k square minus 3k. Now, as usual, we will apply some elementary row operations or column operations. Here we are applying R2 equal to R2 minus 2R1, that is, we want to make this two elements 0. That follows from the conditions of row reduced echelon form. This implies we are subtracting 2 times of element R1 from element of row 2. And similarly the others are as usual, R3 is equal to R3 minus 3R1, and we are getting the resultant matrix as this: 0, 0, 1, 1 minus 5, 1, 2, a minus 3, and here 1, k, k square minus 3k minus 3. Again we will make these two elements 0. So we will get the matrix in row reduced echelon form. So our operations will be R1 equal to R1 minus R2 and R3 is equal to R3 plus 5R2. These meanings are as usual, and we are getting it as 1, 0, 0, 0, 1, 0, minus 1, 2, a plus 7, 1 minus k, k square plus 2k minus 3. Now, here number of equations, that is m is equal to 3 and number of unknowns n is equal to 3. Hence here case 1 is applicable, that we have discussed before. Now the given non-homogeneous system has one solution or unique solution when, as we have seen, rank of A is rank of augmented matrix, that is equal to n. N here is 3, that is 3. Suppose k square plus 2k minus 3 is not equal to 0. Then clearly rank of A bar is 3. But what will happen if A plus 7 is equal to 0? In that case there are two non-zero rows, hence rank of A becomes 2. So these two are not equal. Hence in that case system has no solution. Hence for k square plus 2k minus 3 is not equal to 0, and for A is plus 7 is equal to 0, that is A is equal to minus 7, the system has no solution. Clear? Now when the system will have unique solution, let k square plus 2k as usual is not equal to 0. Then for the system to have a unique solution, rank of A is equal to rank of A bar must be equal to 3. In that case, A plus 7 must be not equal to 0. Then only rank of A becomes 3. Hence for A not equal to minus 7, the system will have unique solution. Now what will happen when the system will have infinitely many solution? The infinite many solution case is that the system is consistent. That is rank of A is rank of equal to rank of augmented matrix. But in that case, this would be less than n, that is equal to 3. Hence, if A plus 7 is equal to 0 and k square plus 2k minus 3 is equal to 0, then we are getting rank of A is equal to 2 and rank of augmented matrix is equal to 2. These two are equal but less than 3. Hence, in that case, the system will have infinitely many solution. Consider this problem. Let the system of equations be this, and we have whether the system of equations, this means solve this system of linear equations. Now first we have to check whether this system is at all consistent or not, and for that we consider the augmented matrix as this: 1 minus 1, 2, 2, 1, 1, minus 1, 2, minus 3, and 10, 2, 2. Applying elementary row operations, we get R2 equal to R2 plus R1. which carries the similar meaning to R1, and we get 1 0 0 2 3 minus 3 minus 1 1 minus 1. Here we are getting 10 12 minus 18. Again we are applying row operations. We are getting the resultant matrix as 1 0 0 2 3 0 minus 1 1 0 10 12 minus 6. Here see that in this case the number of non-zero rows is 2. Hence we can write rank of A is equal to 2. And what is the rank of augmented matrix? Number of non-zero rows 1, 2, 3. So these two are not equal. Hence the system is inconsistent. For problem 3 is for what value of A the system has a solution. This is the system, and we have to calculate the value of A for which the system will have a solution. Now consider the augmented matrix as 2 1 1 3 1 2 0 1 minus 1 4 4 A. Now apply elementary row operations as before. Interchange row 1 and 2 and we get 1 2 1 1 3 2 1 0 minus 1, and here we get 4 4 A. Next apply R2 is equal to R2 minus 2 R1 and R3 is equal to R3 minus R1, and we get the resultant matrix as this 1 1 1 1 minus 2 minus 2, and here we get 4 minus 4 A minus 4. Now we make this element 0. Apply R3 is equal to R3 minus R2, and we get the resultant matrix as 1 0 0 1 1 0 1 minus 1 0, and here 4 minus 4 and A. Here the system will have a solution. We are asked for what value of A the system has a solution. The system has a solution implies for what value of A the system is consistent. Now here number of non-zero rows is 2, so rank of A is 2. But system is consistent if rank of augmented matrix is also 2, which is possible only when A is 0. Otherwise rank of augmented matrix will be 3 and that will not be equal to 2, and in that case system will become inconsistent. So the value of A is A0. Consider problem 4. The value of alpha is unknown. This is the system of linear equations, and it is asked for what value of alpha the system of equations has unique solution. In this case, number of equations is equal to 3 and number of unknowns is equal to 3. Hence, from subcase 1 of case 1 that we have discussed before, here the system will have a unique solution. That means determinant of A is not equal to 0, that is A is non-singular. In that case we have seen before that the system will have an unique solution. Here the coefficient matrix is this 1 1 1 1 2 4 and 2 3 alpha. So the system will have unique solution if determinant of A is not equal to 0, which implies 2 alpha minus 12 minus alpha minus 3 plus 2 into 2 is not equal to 0, which implies alpha is not equal to 5. Hence the system will have an unique solution for any real alpha other than 5. Now the last problem is, how many solutions does the following system of linear equations have? Whether it has infinite solution, no solution, unique solution, or two distinct solution. Here solution is m is equal to 3, n is equal to 2, m is greater than n. So case 3 of is applicable. Augmented matrix, we can write it as -1, 1, 1, 5, -1, 3, -1, 2, 3. R12, we are applying elementary row operations when we are getting 1, -1, 1, -1, 5, 3, 2, -1, 3. Again we are applying elementary row operations, that is R2 is equal to R2 plus R1 and R3 is equal to R3 minus R1. We get 1, 0, 0, -1, 4, 4 and here we are getting 2, 1, 1. Next we are subtracting R3 from R2, R2 from R3 and we are getting 1, 0, 0, -1, 4, 0 and here 2, 1, 0. Now 1/4 R2 is equal to 1, 0, 0, -1, 1, 0 and 2, 1/4, 0. Again we apply is equal to R1 plus R2 to get row reduced echelon form. 1, 0, 0, 0, 1, 0 and where we get 9/4, 1/4, 0. Here rank of A, this 2 is 2 and rank of A bar is 2. Hence the system is consistent. And by applying subcase 1 of case 3, we here see that rank of A is rank of A bar equal to 2, which is less than 3, that is equal to n. Which is equal to n. We are applying subcase 1 of case 3. Hence, we conclude there exists only one solution. So our answer will be C.